Hello everyone, this is Yonggan Fu, a PhD student from the Efficient and Intelligent Computing Lab at Rice University. I will briefly introduce our work, AutoGAN-Distiller, searching to compress generative adversarial networks. Here's the main contents of our presentation, and I will start from the background and motivations of our work. Generative adversarial networks, known as GANs, have empowered many visual applications, and these visual applications have driven the growing demand for running GANs on resource-constrained platforms, such as the online image translation in some apps like Snapchat on your mobile phones, and real-time super resolution for security monitoring on smart cameras. However, there's a huge gap between the SOTA GANs and the edge devices, since SOTA GANs always have large memory consumption and high computation complexity with high energy cost, while edge devices are powered by battery with limited resources and small form factors. Therefore, efficient inference techniques are needed to narrow the gap between them. However, a recent pioneering work in GAN compression pointed out that directly applying conventional filter pruning method on GAN will end in failure, as shown in the figure, due to the vulnerability of the learned mapping between high-dimensional structured image spaces and notorious training instability of GANs. This one pioneering work in GAN compression upon our submission, which achieved promising performance on compressing cycle-GAN. However, the existing GAN compression technique suffers from the following limitations. First, it relies on a cycle consistency loss, which limits its application to cycle GAN only. Second, it relies on a trained discriminator, which is not always realistic in practice. Third, it builds on pruning only, which leaves large room for more aggressive compression when combining with other compression techniques. To tackle the three limitations above, we propose the AutoGAN-Distiller framework, which is the first AutoML framework dedicated to GAN compression alongside the concurrent work. Our AGD framework makes no assumption towards GAN structures, loss forms, nor even the availability of trained discriminators, which significantly trims down the model size and complexity of GANs without degrading performance. Next, I will give a high-level overview of our AGD framework. As shown in the figure, given the task and the user demands for the target efficiency and performance, our AGD framework will automatically searches the optimal GAN structure, balancing the performance and efficiency based on the three customized NAS components listed here. Next, I will give a detailed introduction for each component. First, for the customized search space, our method is motivated by the fact that different tasks will have diverse preference in network architectures. For example, state transfer focuses on consistency of the global style, which prefers shallower network, while image enhancement focuses on pixel-level predictions, which prefers deeper network. It motivates us to instantiate different supernets per application. In other words, we will apply application-specific supernet for the two target tasks. For the image translation task, motivated by the success of cycle GAN, where downsampling upsampling structure is adopted, we follow structure and keep the stem and header network parts for downsampling and upsampling, and search for the backbone network with nine searchable cells, which is sequentially connected. Here, note that we adopt a sequential search space to avoid network fragmentation, which hampers the parallelism on real hardware. And for the super resolution task, motivated by the SOTA manually designed ESR GAN, where residual blocks are adopted, which have higher capacity and are easier to train. We also adopt residual blocks structure, while we replacing the original densely connected blocks with sequentially connected searchable. We will search for both the operator and width for more aggressive compression. And to search the operator, we listed our options here, which are the commonly used efficient building blocks. And to search for the width, it's non-trivial to build independent kernels for different widths due to the exponential possible combinations. Therefore, we instead set a single superkernel with a maximal width, and we search for the expansion ratio to make use of a subset of the dimensions of the superkernel, as shown in the figure. Next is our customized proxy task. So we customize proxy task for both superior performance and efficiency. So here's our objective function. The alpha gamma here are the architectural parameters for operators and widths. And the D here is the distillation loss between the search generator G and the pre-trained SOTA generator. And F here is the computational loss. The next question is how can we design the distillation loss and the computation loss? And for the distillation loss, we just adopt the weighted sum of three kinds of loss, including a content loss to avoid color shift, a perceptual loss to preserve visual and semantic details, and the TV loss to enforce pixel level similarity. And the beta here can be easily determined according to the previous work as elaborated in our paper. And for the computational loss, we decouple it to two parts. That is, we regularize the computational loss related to different architectural parameters with different weight to avoid the architectural collapse phenomenon, which is a bias towards low latency yet low performance models as discussed in a recent ACLEAR paper. And in our case, that here we adopt floats, that is floating point operations. Finally, for the customized search algorithm, we adopt the standard differentiable NAS with three stacks: pre-train, search, and derive. And we also make significant changes for dedicated GAN applications. The first change is that during the pre-training of the supernet, we train each operator with the largest weight, the smallest weight, and to random sampled weights, inspired by the sandwich rule proposed by a recent ICCV paper. The second change is that we apply gobble softmax to sample gamma. That is, only one width is activated during one iteration for saving memory and computation. Then I will show the evaluation results of our AGD framework. We evaluate AGD on two tasks. For unpaired image-to-image translation, we apply AGD on CycleGAN and for commonly used unpaired datasets. And for super resolution task, we apply AGD on ESR-GAN and for commonly used validation dataset for super resolution. For the metrics, we consider both realization effects and the quantitative results. And for the latter one, we focus on both performance and efficiency, including flops, model size, and real device latency. First, we evaluate AGD on unpaired image-to-image translation task. Here, we benchmark over the original CycleGAN and the SOTA GAN compression technique CEC, and we can observe that our AGD achieves the most aggressive compression with the most competitive visual quality. In particular, compared with original CycleGAN, our AGD achieved up to 11.2 times compression in flops and 13.6 times compression in model size, while maintaining comparable visual quality. And compared with the CEC baseline, our AGD achieves notable better visual quality with sharper texture and eliminating color shift. Here's a quantitative result compared with the SOTA baseline CEC and directly applying conventional filter pruning method on the original CycleGAN. And we can see that our AGD framework can consistently achieve the best FID and the best efficiency. And in particular, compared with the strongest baseline CEC, our AGD achieves up to 3.13 reduction in model size and 3.86 times reduction in flops with consistently better FID and notable better visual quality. Next, we evaluate our AGD framework on super resolution task. And here, we benchmark over several SOTA super resolution methods. And note that CEC cannot be directly applied for encoder-decoder GANs due to the reliance on the cycle consistency loss. And here, we zoom in for more details. So you can see that the AGD reduced the model size by over 40 times compared with the original ESR GAN, while maintaining the comparable visual quality. And our AGD also achieves much better visual quality compared with directly applying channel pruning method on the ESR GAN, which has notable blurred textures. And here's the quantitative result compared with SOTA GAN-based super resolution models. We can observe that first, AGD achieves comparable or even better PSNR over the original ESR GAN. Second, AGD achieves consistently superior PSNR with a 3.7 times smaller model size over SR GAN, which is a high performance yet light super resolution model. In summary, we propose the AGD framework, which is the first AutoML framework dedicated to GAN compression. And our AGD framework makes no assumption on GAN structure, loss forms, or the availability of discriminators. And evaluation results show that our AGD outperform the existing options with aggressively reduced flops, model size, and real device latencies without degrading performance. And that's all for the presentation. Thank you.